All right, we're gonna continue with section 10.8. Continue, and let's take a look at some example here. Here come one example. Compute curl f.ds, where f is xz, yz, xy, and S is part of the sphere that lies inside the cylinder. Notice that direct computation used some difficulty. Okay. First one is parameterized S. And then the second one is gonna be you do the curl F. Well, curl F is not too bad, but then you do the dot product. Oh, damn. It's gone crazy. Eh? Yeah. I'm gonna draw out the surface here so you can see what is going on. Not too bad. Direct computation can be difficult because if you parameterize it, it's going to be spherical coordinate, and the dot product is going to be terrible. Everybody know. What we're going to do here is that we're going to use Stoke theorem. I'm going to use Stoke theorem. Okay, so Stoke theorem say that instead of doing this, the flux of curl F we can just do the circulation along the boundary curve C f dot dr. Well, the boundary curve C is this one. If nothing is said about the curve C, then we just assume that it travels counterclockwise. Parametrize curve C. X equal to, well, it is inside the cylinder, so it's got to be a radius is 1, right? Because if you look at the cylinder here, the radius is 1, so it's going to be a cosine t. Y is equal to sine t. But what about z? See, you got to figure out z. Yeah? Well, there's the full circle. So 0 less than equal t less than equal to 2 pi. Intersection, figure it out. The intersection here is the, well, x squared plus y squared plus z squared equal 4. So x squared plus y squared plus z squared equal 4. Now, we have x squared plus y squared equal 1. From cylinder. One plus z squared equal 4. So from here you see that z is equal to, well, it is above the x y plane, so it's going to be a 4 minus 1 is 3, so it's going to be root 3. So RT is cosine t sine t root 3, or prime t is negative sine t cosine t 0, and then f or t. The vector field f is xz, yz, xy. So xz is gonna be a root 3 cosine t, yz root 3 sine t, and then xy cosine t sine t. Now dot them up. F dot or prime t. Well, if we dot them up, oh, look at what we have here. We have a negative 3 plus 3. It's going to be 0. Negative 3, I mean, negative root 3 sine t cosine t plus root 3 sine t cosine t plus 0. So that is just 0, right? Okay. Everybody see this equal sign, right? It's the same equal here. Okay. Now, integral 0 to 2 pi, right? F dot dr. So it's 0 dt. And when you integrate this thing, what do you have? Integral of 0 is going to be
0.
Not necessarily 0. It's going to be c because we don't know what that is. Yeah. C and 2 pi minus 0. So it's going to be c 2 pi. Yeah. It will depend on that number c. Yeah. However you pick it. Well, if you choose c to be 0, then it's going to be 0, 0. Yeah. Because we don't know that c. If you pick c to be 0, then it's going to be 0. Right? Notice that it is possible to have different surfaces share the same curve C. So if this is the case, then the flux of curl F okay, so here come a flux of S1 curl F ds, it would be equal to integral of the curve C F dot dr, and this one is also equal to curl F through the surface S2. So sometimes if it is difficult to parameterize surface S1, right? You can parameterize the surface S2, or you just have to use the Stoke theorem to do the problem. Yeah. F dot dr. I'll put a circle here so you see it's the circulation. Yeah. You want to be clear, then it's going to be a circle right here. Sometimes we put this circle, sometimes we don't. But if it's circulation, usually we have a circle right there, where F is this vector field minus y square x z square, and C is the curve intersecting the plane intersecting the plane y plus z equal 2 and the cylinder x square plus y square equal 1. Cylinder, and then plane gonna cut through this cylinder, so it's gonna be somewhere it's gonna be 2 and 2 right here. Plane gonna cut through. Okay, which means I have to go up here a little bit here. Always do more. Okay, so now I'm gonna draw the intersection of the plane cut in the cylinder. Okay, so plane gonna cut the cylinder. You're gonna have this intersection right here. This curve right here is the curve C. And because nothing to say about the orientation of it, I'm just gonna assume that it has a counterclockwise orientation. Curve C. Okay. We can definitely parameterize the curve C and go through the dot product, which not too bad. However, well, this section is on Stoke theorem, so let's look for the alternative way to do it. Instead of doing the circulation, if we do this instead here, well, we can parameterize S. This is pretty simple to parameterize. Everybody know, because we did this thing before. Hopefully. Right. X equal X, Y equal Y, Z equal fxy equal 2 minus y. Yeah. Ask for the region D. Well, because we parameterize this, the region D is going to be whatever the projection onto the XY plane. And of course, when you project it onto the XY plane, this is the region D right here. You just get a circular disc or XY, right? It's equal to XY 2 minus Y. Right? So or X cross or Y, that's the normal factor. Well, from what we did last time, that would be minus fx minus fy 1. And so this is the taking partial derivative with respect to x, none. Partial derivative with respect to y, negative 1, 1. Oh, how nice. Oh, nice. Fit in right here. Partial x, partial y, partial z. The vector field F minus y square x z square. Now we are very lucky though, because we parameterize S using rectangular coordinate. If we used a different coordinate, then you have to do the substitution after you figure out the curl F, and it may come, maybe difficult. Okay, let's take a look. See what we have here. We have a partial y of z square, so it's 0, 0. So it's going to be 0, right? 0, 0. Oh, so it's going to be 0. Oh, what the heck? 1 and minus, so 1 plus 2y. Yeah. Look like it. Okay. Now we do the curl F dot the normal factor. Oh, look at this thing here. 0, right? Plus 0, plus 1, plus 2y. So 1 plus 2y. Okay. So ready? I'm gonna pour the equal, and this equal here, right down below. It's equal. Okay, it's going to be a double integral over the region D of this one. 1 plus 2y dA. And then 1 plus 2y dA, well, look at the region D. It is in, it's the circular disk, right? So you got to use polar coordinate. Now, 0 to 2 pi, 0 to, actually I'm going to write here, region D here. Huh? dA is all d theta. Radius is, well, it's inside the cylinder up. Radius 1, so 0 to 1. Then got theta is 0 to 2 pi. So 0 to 1. And 1 plus 2. Y is, make sure you get up. You do not use this thing. Where did I? Yeah. You know, even if you parameterize this using something else, you do not use the x and the y up here. Huh? You got to use the x and the y that is in the polar coordinates. So the y has all psi theta. And then all d theta. Just be careful. You can try this out. It's good practice for you guys. Work it out. And you should get the answer to be pi. I have another example that I want to cover for you to see the glory of Stoke theorem. Okay, here come an example so that you can see the glory of Stoke theorem. Yeah. Okay, so if you look up here, right, that is the path that the particle is moving. It is moving in a cycle. Integral C f dot dr, and it is of course along a closed simple piecewise smooth curve. However, we don't want to do this directly. We don't want to compute this directly because we have 4 different paths. Let's see, C1, C2, C3, C4. Too long to compute this directly. Because there are 4 paths. We need to parameterize 4 paths. C1, C2, C3, and C4. So what is the best way to approach this problem here? If you notice that the C here, they do form a surface. Look at the surface. The curve C enclosed a surface as so use Stoke theorem. Now, that's the case that you have to use the Stoke theorem here. Circulation F dot dr. equal surface integral of curl f dot ds, that is the flux of curl f, and then you just have to parameterize the surface s, which is very doable. Yeah, the answer here is 3. Work it out. You're gonna get the answer to be 3. X equal to x equal x, y equal y, and z equal to half of y. Yeah. According to the point, z is half of y. Just look at the point and then you see. Z is half of y. From the 4 points.